Cool. Thanks everybody for coming. This is actually the talk that I was intending to present 2 years ago, which at the last minute I swapped for a latency talk. But don't let that make you think that I actually finished it 2 years ago. I finished it quite a bit more recently. I'm going to be talking about MIMO and easy ways to use it from within GNU Radio. So my first brush with MIMO came, actually I can remember back to when I was in 5th grade, and I was coming home from my friend's house in his parents' car, and they had the radio on, and there were these two flickering amber LEDs next to each other. And I asked what that was, and it turned out it was indicating which of the two antennas on the car was actually being used at that moment to generate the audio. And so that's actually a very early, this was in the 80s, this was early use of selection combining, and that's one of the techniques we'll talk about today. But really the motivation here is that almost all the radios that you guys use all have MIMO, or most of them have MIMO capabilities. Even the original USRP1 from 2004 had MIMO capability from the beginning. But the vast majority of users never use the other channels, or they use it as a place to put their other spare antenna and then swap between them depending on the project. But my goal here is to make it so that we can all get good use out of and easy low barrier to entry use out of those second ports. So first, in any discussion of MIMO, we have to talk about multipath. I'm sure everybody's seen this kind of a picture before, but basically channel RF propagation, you can sort of divide the phenomena into large scale effects, which are the distance and spreading, and then shadowing and absorption, like from trees and things like that. And then the small scale fading, which includes like blockage. Let's say it's a phone, you're holding it in your hand, or your head, there's blockage there. Which will change over time, and so that works into fading. And then there's multipath, and that's really what we're mostly going to talk about today. So multipath is a phenomenon that can be both constructive or destructive. But for the most part, the constructive is not as helpful as the destructive is hurtful in most of our communication systems, and so we really try to mitigate this. And so. But what exactly is multipath? We know it's signals bouncing off of things, and those things can move, and the channel can change. But how do we characterize it? So first, if we start with the main categorization is it frequency selective or flat versus frequency? And then is it rapidly changing or slowly changing? And that'll be on the next slide. So if we look at flat versus frequency selective, we know we have a channel with all these reflections, but those reflections have to travel further than the main ray, and so there's some excess delay. And the maximum excess delay is the worst delay for a measurable multipath component. And so these are typically modeled with tap delay lines, and whether your fading is frequency selective or flat really depends both on how much excess delay there is, but how much bandwidth you're using. So just like as we always see in the Fourier transform, the longer the time, the narrower the frequency. So if you've got a narrower bandwidth that you care about, it's much more likely to be flat fading than if it's wider. Now, so how do we deal with non-flat fading? In many cases, we can ignore it, but usually it should be flattened for optimal performance. Excuse me. So how do we do that? Well, if you've got a single carrier, a single frequency signal, then typically you will use a conventional equalizer, which will try to invert the channel, or it could be a decision feedback equalizer, which has some advantages, things like that. Or you might have a spread spectrum signal, which sort of spreads it so that it's so that the frequency selective effects are not as bad because you sort of average over a wider bandwidth. Or you can use OFDM, and that's actually the most common way to deal with frequency selective multipath is OFDM, because what you're basically doing is you're taking one wide frequency selective channel and turning it into a lot of little, narrow, roughly flat channels. And so for the rest of this talk, we're actually not going to deal much with the frequency selective. It's mostly going to be flat on the assumption that you would, if you had non-flat multipath, you would have fixed it through one of these mechanisms. And then we can really think about it in the flat sense. So now there's the question of constant versus time varying. So this normally characterized with what we call the Doppler frequency, which is sort of similar to Doppler shifting, like from fast-moving objects, but this is more that the multipath components are changing delay and amplitude rapidly, and it sort of looks a little bit like Doppler, but don't confuse it like with the Doppler you see in satellites. So if the Doppler frequency is fast relative to what the sample, the symbol period is, then you have what we call fast fading. But starting from the beginning, we have quasi-static. So that means that the channel may vary, but not during a packet. And you can pretty much estimate the channel at the beginning of the packet, let it ride through, and then only re-estimate it for the next transmission. Next up, there's slow fading, which is during a symbol, it's pretty constant, but during a over a packet, it will change. And so that's the most common that we see. And so you do have to track within the packet. Finally, there's fast fading, where you have the Doppler frequency is much greater than 1 over the symbol time. And so that induces this Doppler modulation. And this really, it makes it no longer a linear time invariant system. It's still linear, but it's now time varying. And it induces the picture, what we see on the right, called the Doppler spectrum. And it's essentially modulating your signal. And when this gets very bad, it becomes very difficult to receive. So how do we model multipath? So there's two main distributions that are used, are the Riceian and the Rayleigh, and they're really just probability distributions. I don't think either Rice or Rayleigh did radio stuff. They were probability guys. But the difference is that Riceian has a line of sight component. And so whereas Rayleigh is no line of sight component. And so what that means is Rayleigh is composed entirely of just the reflections, and you don't have the direct path. In terms of a difference in modeling, they're actually, if you have this K factor, and so if it's 0, it's Rayleigh, and if it's non-zero, it's Riceian, and the stronger K is, the more energy is in the dominant main path, and the less fading you actually get. So a K of infinity is just free space, right? There's no fading at all. And so it's a sort of a sliding scale, but we differentiate between Riceian and Rayleigh. And then there's the Doppler frequencies. That's how quickly it changes. So if you look on the right, this is Riceian, and so you have your dominant main component, and then you have these random paths in addition to it. If this was Rayleigh, you wouldn't have this orange, and everything would be back here. And so the bigger the dominant component is, the less likely you are to go through the origin. But if there is no dominant component, you're very likely to go through origin. That's when you get the really deep fades, when you have a 0 amplitude or close to a 0 amplitude. So, so I'm going to show a demo of this to help us get a feel for it within GNU Radio. So it's a pretty simple flow graph. Unfortunately, it doesn't all fit on the screen, so I'll scroll it for you. But we start with some noise and a constant, and I'll switch back and forth between them with a button. We throttle it, of course. We go through our fading model, which is already in GNU Radio, and thanks to whoever wrote this block, it's really good. I did have one bug fix, but it's really, I was like halfway through making my own and then realized it was in there. So that was a great, great thing to find. So then we convert it to magnitude squared, and essentially get the power of it, and we send it to a histogram and a time sync and a frequency sync. So I'm going to run this, and hopefully we'll see it all on the screen. Okay, we can't see it all at once. Okay. So first we'll start with a constant signal. So we're just sending 1 through the flow graph, and you can see it's just constant here. It's not changing. If I turn on the Doppler frequency, you can see it change. And so the higher the Doppler frequency, the narrower the more rapidly the path changes, right? This is versus time here. So we'll slow it down a little bit. And then as we change the K factor, this is at a K factor of 0. So that's Rayleigh. So it's got really deep fades. You can see occasionally it goes below -40. And as we increase the K factor, you get more and more direct path, and so the fading gets less and less bad until at maximum, I mean, if you made it infinite, this would just be a flat line. And so this is, it sort of shows the continuum of the different types of fading. And then, but if we look at this in the histogram, I'm gonna change the K factor. So this is Rayleigh, and you can see the histogram it's centered around. So all of these are the same total power comes in and out on average, right? Sometimes it's a stronger signal, sometimes it's weaker, but on average it defaults to 0 dB. But you can see, so there's this distribution, and you can get, you have significant content down to -30 that you can see here, but sometimes it's up to, -7, or sorry, +7 or +8 dB. As we increase the K factor, you can see that distribution narrows. And so it's still centered around 0, but it now doesn't get as great on the high side and doesn't get as bad on the low side. And of course, if we make it super high K factor, we basically don't have much multipath, and you can see it gets pretty narrow. So now I'm going to switch over to a noise-like waveform and lower the Doppler frequency, or actually I'm going to turn the Doppler frequency to 0. I'm going to put the K factor pretty low so that we can see this. And we can see this is flat fading because because we have no time delay. This is all of those taps in that tap delay line are all at time 0. So we can see that this is flat. And if we turn up the averaging here, you can see that it comes out to flat, right? Now, if we go back to a single tone, right, you can see there's a single tone. But as we turn up our Doppler frequency, wish this could all be seen at once, you can see, let's turn up the Doppler frequency some more. And I got to turn up turn down the averaging. So here what you can see is this is that Doppler spectrum, sometimes called the Jakes spectrum. And you can see here's our dominant tone right at the middle. Oops. And then these are the varying tones. Now there's 8 of these because there's 8 selected in the model, but you can see that this bandwidth is essentially what I'm setting at the top here. So if I reduce that Doppler frequency, right, this gets narrower. This is all still flat fading, but it's frequency varying, and so it causes this content in the frequency domain. So now if we go back here and we switch away from the flat model and into the frequency selective model, you'll see similar. So let's turn up Doppler, K factor. And if we look, and we'll turn this, now we'll do it with noise. And let's turn the Doppler off. And now you'll see that it's non-flat. And that's because that block is introducing time delay before all of those or in between all of those taps. Now, of course, if we turn the Doppler away from 0, it's going to change fast enough you can't really see it, but it is non-flat in there. And it really just depends on how fast you make the channel. But you can see it's non-flat, but it's changing. So, and again, we have the same distribution here. And the same dependence on K factor, but now it's frequency selective. So that's actually going to be the last frequency selective that I show during this demo. Everything else is going to be frequency flat because we'll assume you used OFDM or some other technique to flatten out. Okay, so that's how we model multipath. So now we come to MIMO finally. So this is the canonical MIMO drawing, courtesy of Wikipedia. But the idea is you have multiple transmitters and multiple receivers. And so, and when they say MIMO, multiple input, multiple output, it refers to inputs to the channel, basically how many transmitters you have, and outputs from the channel, how many receivers you have. And you, of course, all of them couple to each other, but in varying amounts. And that's the coupling or the path loss, and it's denoted with H. So H11 is from antenna 1 to antenna 2. H21 is antenna 1 to antenna 2. That's how that works. And now we end up with a lot of matrix math at this point because it makes all of this easier. But so effectively, you have multiple channels between your various transmit antennas and your various receive antennas. But those channels can be correlated, and sometimes they're correlated and sometimes they're not. In general, the further apart the antennas are relative to a wavelength and relative to the physical things that are causing the reflections, the less your gains will be correlated between each other. And of course, if it's free space, everything will be totally correlated because there's no other effects. And we can also get diversity through polarization. Of course, that's limited to two ways, either horizontal, vertical, or left, right. But that can be useful at small numbers. And so the terminology, as I say, there follows the channel. If you're pedantic, SIMO is one transmit, and MISO is one receive. And so now I'm going to show a similar flow graph, except this time it is with MIMO. And so it's really the same flow graph, except we have two of these fading models, and they're completely decorrelated. But then I have this matrix multiply here, which is fed by a correlation matrix. And so when the correlation factor is 1, each output is basically the two signals, the two matrices added together. And when the correlation factor is 0, they're totally independent. And then we again take the complex to mag squared and show the amplitudes versus time. In this, I no longer show frequency because it's flat in frequency. We're not doing we're not doing the frequency selective channels. So it simplifies the display a little bit to not have that second thing. So okay, so here we'll turn up the Doppler frequency, right? And now you can see this is the channel gain versus time versus for the two different paths. So you have signal 1 and signal 2. Now this is with correlation of 0, and the correlation slider is down here, unfortunately. But as I increase the correlation up to 1, you can see they become the same. And then if you're somewhere in the middle, like 0.7, right, you can sort of see similarity, but they're not exactly the same. So you'll never see exact perfect correlation. And in terms of using MIMO techniques, the lower the correlation, the better, because you get more diversity out of it. But in general, you can get useful results, down to moderate correlations of 0.5 or so. And now, if you don't have, if you do have perfect correlation, as if it was free space or some other situation where you happen to have the antennas too close to each other, then you won't get the same level of improvement from MIMO, but you may still. Oh, let's scroll down here. Okay, so good. So that's basically the modeling of the systems that we're working in now, and so that's what MIMO propagation looks like. And there's other models that are more complicated, but this has really the basics. So in the rest of the talk, I'm going to go through a model communication system. And now this is like a full communication system here, right? You start with source coding, channel coding, modulation, all that stuff, and in some situations you'll have different, you may reorder these blocks, but basically you have channel coding, modulation. You would add your MIMO encoding, then your channelization, whether it's OFDM, root raised cosine filtering, spreading, whatever it is. And then we have the propagation loss and multipath. And then at the receiver, you get your AWGN, right? And that's why your noise should be decorrelated between the two receivers, because it's really receiver noise. Even if it's thermal noise, atmospheric noise, the antennas, as long as they're not highly directional, large, like SETI kind of antennas, they will have independent noise. When they don't have independent noise in radio astronomy, it's because you're doing, or you're attempting to do interferometry, and you don't want it. You do want the correlation, and that's how you control the direction. But if for our purposes, you can assume the noise is decorrelated here. So then you would do time and frequency sync, dechannel it, and you reverse everything else from the above. So what I'm going to concentrate on today is the stuff that's not blackened there. So we have modulation, MIMO encoding, the propagation, AWGN, and then the decoding and demodulation. We left out the channelization, And I left out the time sync. I know that's something I've said, you never leave out the synchronization, because that's the hard part, but the textbooks leave it out. We're going to leave it out today for our purposes, but it's of course important. But all of these flow graphs have the timing synchronization automatically in there. We still do carrier recovery, but we don't do the timing recovery. So going back to MIMO, so why do we use MIMO techniques? First, increased reliability. We effectively get antenna gain. At the very least, we effectively get antenna gain through our MIMO techniques, and we can increase throughput. We get path diversity, more reliability, etc. Why wouldn't we? Well, there's hardware complexity involved. You have to have multiple receive chains, multiple transmit chains. There's significant algorithmic complexity and processing that goes along with it. Sometimes, depending on which MIMO methods you're using, you need to pass channel state information. What this means is the receiver needs to report to the transmitter what the channel is looking like, so that the transmitter can act on that appropriately. We'll get a little more into that, but this overhead can actually be significant if the link is bad and you're really trying to optimize your MIMO complexity, and often this CSI feedback is a limiting factor. And now, another reason you might also not want to use MIMO is if you have a free space system, then true phase array beamforming is much easier. You could do it in the analog domain, or the math is easier even if you do it in the digital domain, and you can point beams. And if there's no multipath, you're going to get the same results as if you just did beamforming. So that's easier in those situations. So to divide up the various techniques, we have receive diversity, and we'll go over three different varieties of that. There's antenna selection, equal gain combining, maximal ratio combining. There's transmit diversity, where we also have similar options. We have space-time coding, which we'll show an example of that as well. And sort of the true MIMO, the sort of advanced MIMO stuff, where you would have what's called spatial multiplexing or precoding, and there's a bunch of other techniques around that, and we'll cover that a little. We don't have a demo of those. And then there's massive MIMO, and I'll cover a little bit of that at the end. So I've talked a lot about diversity, but what does that really mean? So we kind of intuitively know that diversity in paths means that if one's bad, the other might be good, right? And so we can still communicate in that situation. So, but it's actually it can be quantified too. It's not just this sort of fuzzy concept. And so we have what's called diversity order, and if you're able to extract the full diversity, it will improve your links in these fading scenarios. So this is just a plot of a simple communication system, and you probably can't tell the colors very well, but this line here is the bit error rate for this communication system versus in just a Gaussian channel with no fading. And you can see has that characteristic rapid drop off as the SNR increases. And so it just takes a little bit of increased SNR to radically drop your bit error rate. But when you have a faded channel, it turns out that it's not. You lose that steep slope. And now why is that? Right? We're basically saying that whereas before a 1 dB could give you a huge drop off, now it takes many dB to get the same kind of drop off. So why is that? Well, if you have fades of 30 dB, then adding one, that are 5% of the time, let's say, adding 1 dB will maybe you'll have those fades, 4.9% of the time, right? You won't get the same advantage. It's almost like you have something, it's effectively binary, either the channel's there or it's not. And so you get these deep fades, and thus you have to add lots of SNR in order to really get the low bit error rates, right? And this is the primary problem of fading channels. And this becomes, rather than this sort of logarithmic drop-off or exponential drop-off, becomes a very linear drop-off. So what happens when we add diversity? So if we can get full diversity of order 2, then you can see we can go from here to this line. Now, what is this saying? This is saying if there was maybe a 5% chance of one of these deep fades that you can't deal with one antenna, but if they're totally uncorrelated, well, the chance of them both being deeply faded at once is 0.05 times 0.05, right? It becomes a much smaller number. And so the more diversity you have, the closer you can get to the ideal curve, right? So this is with 2, this is with 4. Now you can get this diversity on the transmit side, on the receive side, or you can get it as a combination. But diversity 2, you should think of as it's 2 receivers or it's 2 transmitters. Diversity 4 could either be 4 receivers, it could be 4 transmitters, which is less common, or you might have 2 of each, right? But as the numbers go up, your diversity is basically how many independent paths you have. So, right, the chance of all 4 of those, if they're totally independent paths, being deeply faded is extremely low, and that's what we're showing here. So, so that's what we mean when we talk about the diversity number. And if you're good at your mechanisms, whether you're doing selection or equal gain combining, if you do them right, you'll get that full diversity. So. So here I list 3 different mechanisms to achieve diversity. One is antenna selection, which in code is just, take the stronger of A or B, right? So it's pretty easy. And actually usually, and that's what my friend's parents' car had when I was a kid. But it's really easy. And typically if you're doing this, you're usually doing it entirely analog. You're not doing it in code like this, because if you've gone to the effort of getting 2 signals into the radio, you wouldn't bother using this method. But if you have, say, 2 power detectors, you can rapidly switch between the 2 signals, and that's what their car radio was doing. And you kind of have to track the carrier, because when you switch between the 2, it'll glitch, and if it's FM, you'd hear a little click but in general, it's a very easy system. Then we have what's called equal gain combining. You just add the 2 together. Again, you have to track the carriers, or if you add them together, they won't line up. But if you're tracking both carriers and you add them, that improves the signal, because you're adding the signal from both of them, and they add in power. They add in voltage, which is better, and the noises will add in power, and so you will get a net gain there. And so that's equal gain combining. Then there's maximal ratio combining, which is provably optimum, where the stronger where you add them, but you apply gain to the stronger signal, not the weaker one. So if one is twice as strong as the other, when you add them together, you first multiply that one by 2, and that emphasizes the stronger one. And it turns out that's the exact same math that happens in beamforming. And so, except this is sort of adaptive, so you don't have to know I'm pointing in this direction. And in multipath, it doesn't form like a direct beam, but it's effectively the same thing. And you're beam forming, and so you get 3 dB of antenna gain if you do this. You get almost 3 dB probably if you're equal gain. It depends on the statistics, but maximal ratio will get you the full 3 dB if there's no fading. So even if there's no fading, these are useful because you're collecting twice as much energy, right? You have 2 antennas. So you have 2 buckets, and you can add that energy together if you do it properly. But when there's, of course, multipath, then the benefit is much larger, right? And so that's what I'll show in a moment. But again, maximal ratio, you not only have to track the carrier, you have to estimate the SNR, which is actually not always that easy, especially at low SNRs. So I'm going to show a flow graph that demonstrates that. Actually, before I show that, I'm going to show, my tabs got rearranged here. So I'll just show the blocks I made. So equal gain combining is easy, right? It comes in, you add them together. It's already carrier synchronized before this, right? So this one was very straightforward. Selection combining, it's a little more complicated in the flow graph because I tried to do it without writing code, and it's hard to find something that will say, oh, this one's stronger, pick it. So, but effectively all this, math in there is just figuring out which one is stronger. The argmax block is doing that, and then we're choosing which one to pass through to the output. So that's selection combining. And these are both, I'm doing all 2-way here, but all these can be, increased to 4-way, 8-way, however many you want. And of course, selection combining will continue to lose to the others because the others are actually adding all the energy, where this is just picking one and you won't get any antenna gain, you'll just get the diversity. And then we have maximal ratio combining, which is the most conceptually complex and algorithmically complex, but it's the block diagram's a little bit simpler. But essentially, we're measuring and then averaging the incoming signal levels and then multiplying those signal levels times that. Now, you also really are supposed to track the noise, but the noise is, in these situations, the noise is the same. So it simplifies it a little bit. Ideally, this would be written just out in code, but this is yeah, I kind of like to see it as a flow graph, right? So we have the two signals coming in, and they pass through these multiply blocks and added together, and then they're scaled by the sum of the powers, and then comes out, and then this stuff up here is just the power estimation, the SNR estimation. So here's the flow graph that uses this. So we start with just a audio source. It generates, it converts to bits, right? We convert those bits to plus and minus ones. So this is all BPSK. All of this works BPSK, QPSK, QAM, whatever. But we're doing all BPSK here today. And now I put a little bit carrier in here because we have to estimate the carrier. We have to synchronize. So I add a carrier by muxing in some ones. Every eight useful bits, I have one bit of pilot. And so we send that through this correlated Rayleigh channel. Same thing goes to both of them, but it's two different channels. So this is transmit, this is over the air. And then on the receivers, right, we have two receivers. So we demux the carriers, and the carriers go into these carrier regeneration blocks. The carrier goes into the carrier regeneration block, which we then multiply conjugate to take that back out of the signal. And so we've transformed back to DC. And then we put it through the three methods: equal gain, maximal ratio, and selection combining. And we can output it to audio, but we can also show the constellation. And I'll show the 5. It's easier to see on the 3, but we'll start with the 5, and then but the display is pretty busy. So anyway, so going back here, we also show the direct paths without the as if you just had one reception. So we'll run this. And so we can add noise here, right? We can add more noise or less. So this is a decent amount. Doppler will change the channel, and you can see it moving around. We'll leave it there. We can correlate it, and you can see how. Here, let's turn the Doppler on, and I'll also turn the K factor down, right? So here we've got multipath. Now you're seeing 5 things there, right? So path 1 is blue. Now you don't really see the blue much because it's followed by the selection a lot. But path 2, and then the green is equal gain combining, and the purple is the maximal ratio combining. So you can see even when like the blue fades and the red doesn't, or the red fades and the blue doesn't, the green and the purple stay pretty good, right? And let me make that a little worse so you can see it better here. Right, you can see everything's moving around, but the green and the purple move around a lot less. So it's a little hard to see here, but so I'm gonna switch over to just so show 3 of them at once. And I think this is equal gain combining. Yeah, so this is the equal gain combining. Okay, so now you can see. Let me turn up the Doppler. It's changing, and the K factor. Right, you can see that sometimes the red is bad, sometimes the blue is bad, but the green is always pretty decent, except when both the red and the blue go into the middle, right? But now if we were in a correlated setup, where the two antennas are too close to each other and they're no longer independent, the green fades with it, right? So we no longer get our diversity, and the green is staying there. Now, I'm going to turn the Doppler down just to make this display. Now, one thing you can see is, if I can turn this down, there we go. If we zoom in, or actually maybe in too far in, you can see here it's kind of subtle, but the red and the blue are further out than the green. And that's the 3 dB you get from the antenna gain in the fully correlated case, right? Normally, if we had selection here, and the selection would just go out as far as the red and the blue did, right? Because it would not be combining the energy of the two. But here we combine the energy and we scaled it back, and that's why you see that the green is better. So that's our antenna gain in the case of no, essentially the no multipath. Right, now let's go back to the Doppler, and right, and you can see it's still, even when they're together, sorry, in the case of full correlation, even when they're together, the green is better, but when there's no correlation, right, you get the much better setup. Does anybody have any questions on any of that to this point? Okay, good. So that's the correlation. That's the received diversity, and now I'm just going to I'm gonna switch this over to audio, so it's not just the constellation display, but it's audio. So I want you to listen closely so you hear the effects of the fading over time and how it affects the audio. So you can see actually if we turn up the correlation and we make the fading bad, as it drops out, you'll hear, and of course we have too little noise here. If you get more noise, you'll start to hear it click. But that's pretty good there. That's with high correlation. Here, I should do it like this. So that's a lot of noise, and so right, you're starting to hear it go bad there, but it's still here. You can still hear it. But when we turn up the correlation, right, you lose it, right? Because what we're having there is again, when it's not correlated, we get the gain of the diversity gain, and when it is correlated, you lose that. You still get your 3 dB of antenna gain, which is why we were able to go to such a bad SNR and still hear it. So okay, so that was receive diversity. So now let's go to transmit diversity. Okay, so now transmit diversity is actually incredibly similar. You have antenna selection, which you choose, and again you get no gain because of that. No power gain, no diversity gain, no antenna gain, but you do get diversity gain. The downside of this versus the receive stuff is that the receiver has to tell the transmitter which is the better antenna at any point. So the higher the Doppler rate, the more bits per second are wasted in the reverse to tell the transmitter which antenna to choose. But it's it's 1 bit. But now if the channel is very slow, that you could send a bit every every second or so, right? Whereas if it's very fast, it has to be quicker. And at some point, it changes quicker than your latency of the link, and you can't do that. And it doesn't provide any gain. The other choice is maximal ratio transmission, which is really is the reverse of MRC, and it gives the same diversity gain, but which is transmit beamforming, and so it provides antenna gain. So again, if you were to measure this, you would actually, if you were to look at it in free space with the 2 coefficients, you are effectively pointing a beam. Now with only 2 antennas, it's not much of a beam, right? But you're providing gain in one direction. And if it's more antennas, it would be a finer and finer beam. Now, if there's other techniques beyond this, both for MRC and MRT, sometimes if there's interference rather than just noise that you're worried about, it can be better to sacrifice a little bit of gain that you get from MRC or MRT, which is the maximum gain. Sometimes you sacrifice a little bit of gain in exchange for putting a null on the interferer. Now, if it's just Gaussian noise, there's no concept of that because it's uniform. But if there is an interferer that you want to get rid of, you can use these, and they're called zero forcing techniques. But it's essentially just pointing a null in the direction of the interferer, and you can point 1 null for every extra antenna you have. And so, but that's of course, certainly in the case of TX diversity, needs a lot more channel state information, right? The MRT and that would require a lot of CSI. But often like cell phone systems have used this for quite a while. Even Wi-Fi will sometimes use channel state information depending on the mode, and so that the transmitter can point the signal where it wants. Okay, so next we come to space-time coding. Now, the great thing about space-time coding is that it doesn't require channel state information at the transmitter. Yet the transmitter can do MIMO with it. And so what this means is, because it's no channel state information, the transmitter doesn't know how to point the energy in the right direction. So there's no antenna gain from this, but you still can get the diversity gain. And so the way you do that, the easy way, the first way that was discovered to do this is called Almood encoding, and the general family of these things is called space-time block coding. Or if you do it in OFDM and you put rather than, so space-time block coding means the code symbols you do sequentially, so A then B, A then B. Whereas space frequency block coding would mean you just put them on adjacent carriers in the in your OFDM, but it's the same math. And so and you could actually do it in CDMA. I've never seen anybody actually do it, but there's no reason you couldn't. There's two orthogonal signals. You can just do that in the coding domain as well. So anyway, Almood encoding is as close to you get sort of to a free lunch in comm systems. You get but if you have only two antennas, you can do full rate, which means you don't give up any data rate and you don't widen your bandwidth. You get the same data rate through, and it's fully orthogonal, which means you would get the full diversity gain of the system, and there's no impact of one symbol on another. It's been extended beyond two antennas, but you have to give somewhere. You either have to accept reduced orthogonality or reduced diversity, or slow down the data rate so that you can do this, because it doesn't perfectly scale. But there are some versions that go up to like 4 antennas, 8 antennas. Like Wi-Fi has I think a 4 and an 8 antenna, or 3 and a 4 and maybe an 8 antenna version in there. So, but you give up a little. But in any case, the idea is, if you look at this matrix, you have C1 and C2, which means that so the columns are your antennas and the rows are your time slots. So let's say I have 2 bits that I would normally send, called C1 and C2. I would send C1 and then I would send C2. So instead, I send C1 and C2 at the same time, but on different antennas. And then the next time period, I send the negative conjugate of C2 from the first antenna and the conjugate of C1 on the second antenna. Now, what this means is that each symbol is going on both antennas, but it also means you have two bits in 2 times, and so we don't lose any data rate. That's why this is called a full rate code. So what this does is now the receiver gets a picture of both signals coming from across both paths. And so there's a sort of a matrix inversion you can do that gets the symbol separated again, right? Because they're mixed here, but then you would get it separated again and be able to separate them at the receiver. So I'm going to show this. So we can do, this is the Almood encoder, which is basically just that matrix, that matrix that I showed you, where you source in, I multiply by half, right? Because you don't want, cheat. You have, if you have 1 watt on one antenna, you have to go to half a watt on each to make the math fair, right? Now, if you happen to be limited by antenna power, then by amplifier power, then adding a second one gets you more power. But that's cheating in the comm system sense, right? You have to divide the power equally between the two. So we separate the streams, and so we do the math on them, and so you take pairs of symbols essentially that come out of the 2 ports of the stream to streams. One goes back in and then the other is basically this does the math on it. It does that complex conjugate and takes the so the C1, right? So this is easier if I do it this way. So C1 would come out here and would come out the first antenna at the first time period. C2 would come out the second antenna at the first time period. And then the processed ones cross, right? You cross the streams here. It's allowed in this case. Complex conjugate, and then you multiply by -1, and this one's just complex conjugate. And those become the second symbol on the two respective antennas. So that was easy to do in GNU Radio in using hierarchical blocks. The receive is more complicated, and I just went to math in Python for that. So first we have to estimate the channel. So this is just a Python block. I don't know if you can see it, but basically we have the constructor, and we just have this matrix that is the known symbol that we send in the pilot, right? So we just send a 1-1 in the pilot, and that gets Almood encoded along with all the data. And so here this is the matrix that we're going to need to invert it, and then every time we receive, we basically multiply by the inverted thing, and that tells us what the channel coefficients are from the two antennas to R1, right? Remember, this is single receive in this example. And then the actual receiver then takes those estimated channel vectors, channel coefficients. It makes its own vector out of them, inverts that, and then that gets multiplied by the incoming signal, and then that comes out. And so if we look at that in the Almood demo, right? So we again have our data source. We go to the Almood encoder, and we have channel gains for the two separate channels, and then we add in noise. And then on the receive side, we're demuxing out the pilots, right? So the pilots get demuxed out. They go to the estimator, and it has an alpha, so you can average the estimates over time periods, although I didn't implement that part yet. So it's not averaging them. So you'll see the noise grows a little bit, and I'll point that out. And then we display the estimates, and then it goes into the receiver. The same estimates go into the H path on the receiver, and the data comes into the in path on the receiver, and it demodulates it and comes out, and it'll show it as as a constellation. So turn the noise down a little bit. So here you can see this upper one is this is the estimates. So here I'm setting the path gains, right? And you can see it's estimating the path gains. That's H2, that's H1, right? And you can, even if you have one path gain is off, right? Essentially, you disconnected one antenna and you only have signal coming through the other. There's still enough information there for the receiver to receive it, right? That's the I unhook the antenna version, or I've got two uncorrelated paths and one is incredibly bad, right? So you could still receive it. You won't get the improvement in that case, but at some other time, then a different one will go to 0. Now, if I happen to pull both of these to 0, the flow graph dies because it's a singular matrix, and I need to catch that as an exception. But you could see what it does here, and then down here you could see the blue is what comes into the antenna, right? And you can see it's got this weird point in the middle. That's because we're summing both signals coming in, and so so sometimes one's positive, one's negative, and they go to the center, right? So you obviously can't just decode. You have to do the math to decode it, and that's what the red is, right? But if I were to change this, you could see that, right, the two different paths have two different gains, and that's why the blue sort of bifurcates like that, but the red stays correct because it's estimated. Now, I'm going to turn the noise up a little. So now I turned the noise up, and now as we drop the amplitude of the path gains, right, you're going to see that it all gets equalized. So the red signal amplitude stays the same, but the noise amplitude grows because, right, we have worse and worse channels, right? But what you see is when one is really bad and the other one's good, we've got a good signal, and if the other one's really good, we still have a good signal. But as they both approach 0, that's when it goes bad. So obviously when you have if it's either highly correlated or they both happen to go to poor paths at the same time, that's when the diversity is not sufficient. And it's not magical. It's not going to decode a signal from nothingness. So that's the Almood demo. Any questions so far? Okay. almost done here. So that's the space-time coding. I didn't, there's the more complicated versions with more antennas, but that's, the same basic concept. Now, I don't have demos for the rest of it, but we'll talk a little bit about the more advanced MIMO stuff. So the first technique is called precoding. And this is basically the transmitter is able to, yes, 5 minutes? Okay. So in this method, the transmitter knows what the receiver channel is, but there's multiple antennas on each side, so the transmitter has to know all of those coefficients. So if the transmitter has 4 antennas and the receiver has 4, that's 16 coefficients that have to somehow be communicated to the transmitter. But once it knows those coefficients, it's able to do, and usually it uses a singular value decomposition to do this, but you're able to figure out which what sort of precoding matrix, what to multiply the transmitted signals by in order to send energy to particular paths. And so you can effectively create the minimum of the M and N parallel channels here, right? And you can direct energy to each of them that will be coherently received at the other side. And this other side still has multiple antennas so that, because there's separate channels that may land on one or the other. And so it also gets diversity. But you can, but also in a frequency selective situation, it may also be doing this in the frequency domain. And so it's directing energy not just to particular paths physically, but also into particular frequencies, right? So if you have one frequency with a null, there's no point in sending energy there. So precoding will put it in a band that's good. So that's how you could take advantage of the improvement of the SNR when the fading is in your favor, right? When it goes above the 0 line, this helps you take advantage of that. So this is more complicated. It's and I have some Python code that does it, but it doesn't work. It didn't get it into the demo. But this allows an increase in the bit rate, both because you have stronger channels and also you have multiple channels, right? You can send multiple things at once. And this, of course, can also be used with what's called multi-user MIMO, where you're sending different things to different users at the same time. Again, by having different precoding matrices to transmit to each one. So of course that needs a lot of CSI. So the final technique that I list here is called spatial multiplexing. And the advantage of spatial multiplexing is you don't need any channel state, and the transmitter can essentially just sends a separate stream on each antenna. And it's up to the receiver to figure it out. And this is also, there's modes for this spatial multiplexing in Wi-Fi as well, in the newer ones. And so if you have 8 antennas on the transmitter and 4 antennas on the receiver, you can send 4 streams to that user. If you have 8 on each end, you can send 8 parallel streams. Now, it turns out that even if there's a lot of multipath, you don't really have 8 good channels. Or if there's 8 and 8, you'll have some number less than that. So typically there's like one super strong channel and then some others. But with spatial multiplexing, you can't choose that, right? So you have to sort of code across it. Whereas with precoding, you can choose, this one channel is really good. I'm going to put all my energy there. And this other channel is not as good. I'll only do BPSK on that channel or something like that. So spatial multiplexing really, on the other hand, leaves it up to the receiver to decode. And this is where you hear about sphere decoders and things like that. Essentially, the receiver has, if there's 4 transmitter antennas and 4 receive antennas, and all signals are sent at the same time, on each receive antenna, it'll receive all 4 of those streams. But because it has 4 pictures of it with different relative phases on each, if there's enough multipath diversity, it's able to decode that and separate them. But certainly it would be always advantageous to use precoding if you had the CSI in order to do that. But of course that's not always available. So the final technique is Massive MIMO, and this is a picture I've used many times as a setup at the University of Lund in Sweden, where they had 64 X310s, which each had 2 antennas. So it was 100. Was it? No. Yeah, it was a 128-way MIMO. And in Massive MIMO, typically it's not 128 on each side. It's a 128 or 64 or 32 on one side, and then it's like a handheld with 1 or 2 antennas on the other side. But what you have here is you have this continuous CSI feedback, and the antenna is essentially attempting to invert the channel. so that it can put a beam right at one user. Now, these beams may not be sort of a fan beam, like a directional beam, like you're thinking of when I say beam. It can actually be more of a cloud, right? If it's very diverse multipath, it won't be a straight path. It will be, you know, everything combines coherently here, and even right behind it, it might not. And so as you move, it has to keep adjusting. So there's a lot of CSI to do that. And so I call that eigen beamforming versus, you know, conventional beamforming. But again, if there's no multipath, this would just, you know, sort of collapse down to a phased array antenna. And there's a couple of methods. You know, MRC and MRT just aim as much energy as possible to a certain point. But then there's also zero forcing or null steering, which also tries to make, at one user, it sends, you know, a cloud to them, but also nulls out every other user's signal at that place. And so that's a lot more computation, and you know, so there's a big pile of FPGAs underneath that does all of that all those combinations in this. But you're able to effectively create individual clouds for each user, and it just as they move around or as the channel changes, you have to keep adapting. So unfortunately, we don't have a demo of that. That's wouldn't fit in the overhead. So so anyway, that's what I've got on MIMO. Are there any questions? Silence. Okay. Well, thank you.